So we got to start somewhere. A unit on measurement is a good place to start. It sets up a lot of the skills that you guys are going to need throughout the semester when we actually dig into the physics. So here we go. Measurement. In physics in the whole world, everywhere in the world, even though there are countries that don't use it, we use the SI system. There is an international scientific system established by the French. That's why it's SI, not IS, because it's Système du International, not the international system. And there are base units for everything. What is the base unit for length? It's not the centimeter. It is the meter. Meter spelled M-E-T-R-E. M-E-T-E-R is something else. The meter, the symbol for meter is M. Nothing overly shocking, I hope, at this point. Mass, the unit of mass is the kilogram. Even though there is a base subunit there, the gram is technically, I mean, the base of that name is gram. Kilogram in physics is what everything gets converted into. The base unit for time is the, what's the fundamental unit for time? It is the second. Letter S. Speed. Speed is one of these compound units. Kilometers per hour is what you guys are conventionally used to. It is not kilometers per hour. It is meters per second. Kilometers per hour is what you're used to. Obviously, it's what we use on the roads here because meters per second are, as far as regular street driving, a little bit ridiculous as far as units go. But for the stuff that we measure, whether that's really, really slow stuff or really, really fast stuff, the meter per second is a lot more useful, and the meter and the second are both fundamental units in the SI system. So speed measured in meters per second, M/S. And there's some other fundamental units that we're going to talk about. We talk about forces, we talk about energy. One of the energy you should have seen in Science 10, depending on who your Science 10 teacher was. If you had me, we didn't do it. If you had Easton, I know you do. I think everyone else does. I do astronomy instead. Fundamental unit for energy is what? It's the joule. Joule. Capital letter J. And forces are something else that we measure in physics. We'll spend a whole unit on force, a long time talking about different kinds of forces. Does anyone know the unit for force? It is, in fact, the Newton. Named after probably one of the most important people who's ever lived. Capital letter N. And now we're going to be working in all of these units and more. There's other stuff that we're going to look at. But these are the fundamental ones. And so we're going to look at converting back and forth between different sizes of these units. And the different sizes of these units all have a set of prefixes. The only one that already has the prefix is, when I say prefix, I mean these guys here. A kilogram. Kilo means what? 1,000. It's 1,000 of something. So if you have a kilogram, even though gram is not the fundamental unit here, if you have a kilogram, it means you've got 1,000 grams. So these prefixes already exist. Some of them you are familiar with. If you're into computers, you're going to be familiar with a few more. These ones, they're on your formula sheet, are the ones that I'm going to have you guys moving back and forth between. If you aren't into computing, then the ones you're probably familiar with are kilo, centi, and milli, and that's it. The kilometer or the kilogram, the centimeter, the millimeter, or the milligram. But if you're into computing, then kilo, mega, giga, and tera are something you're probably familiar with. A terabyte, a gigabyte, a megabyte, a kilobyte. Storage capacity. If you've studied chemistry or you are into physics and you've done some reading on your own, then micro and nano for sure are ones that you've probably seen. Micrometers, nanometers, but they get a lot smaller. Pico and femto are two that we use in physics somewhat regularly, depending on your field of physics. The ones that I've highlighted here in pink are the most common ones that get used day to day, but all of them have prefixes. So the symbol for micro, I'll give you a bunch of these on here. The symbol for micro is this cool Greek letter mu, which that's a scripty kind of M. It's not a U. And, you know, to cause great confusion, this is going to show up later meaning something else. But at this stage, this symbol is going to mean micro. So if I have a micrometer, it would be this symbol followed by that symbol, the letter M. And micro means you have 10 to the negative 6 of something, or 1/1,000,000th. 6. Milli is the prefix M. It's 10 to the negative 3, or 1/1000th of something. Centi is the letter C. That prefix means you have 10 to the negative 2, or 1/100th of something. So a centimeter, there are 100 centimeters in a meter because centi means 1/100th. If there is no prefix, you just have one of that thing. Kilo is K, mega is a capital M, kilo is 10 to the 3, or 1,000 of something, as you guys have already said. Mega is 10 to the 6, or 1,000,000 of something. And then the other ones are found on your formula sheet. I don't need to give you all of them. So there is a convenient method to convert back and forth between these units and between other kinds of units. That method has a name. Does anyone know what it's called? It's called different things by different teachers. Did anyone take chemistry for a semester? Okay. If you did any stoichiometry, you use this method aggressively. They might not have called it that, but that's really all it is. Stoichiometry is just an exercise in converting between units, whether it's density, mass, volume of something, moles of something. All you're doing is swapping out units. So if stoichiometry was difficult for you, well, let's try it again. So in math and physics, this is called the factor label method. And we use it to convert units easily. So if I wanted to convert 165 millimeters to meters, for lots of you, this wouldn't necessarily be overly difficult. You'd say, okay, well, milli means 1,000. I'm just going to divide by 1,000 and call it a day. But we're going to use some of these easier ones, to give a method for when things get more difficult. So I'll show you what I mean. The factor label method says if we're going to start with, if I want to convert something, I pick the thing I want to convert. I want 165 millimeters, and I want to turn that into something else. In this case, I want to turn it into meters. So again, lots of you are going to be able to do this relatively quickly, but here's the method. What we're going to do is we're going to start to convert these things. We're going to multiply by a bunch of fractions. As many fractions as it takes to go back and forth between these units. In this case, we only need to go back and forth between one because there is a nice conversion between millimeters and meters. Now, how you fill in this fraction is the thing that you have that you want to get rid of goes in the opposite location that it's already in. Here's what I mean by that. This 165 millimeters, I could write that as 165 millimeters over 1. If I wanted to take a whole number and put it as a fraction, I could write it as 165 over 1. And so if I did that, then this millimeter would show up in the numerator. And so to get rid of it, I need to multiply by the fraction that has millimeter in the denominator. Because when I'm multiplying fractions, I'm just going to go across the top, I'm going to go across the bottom. I'm going to end up with millimeters in the numerator and the denominator. And when I have the same thing in the numerator as I do in the denominator, what do? They cancel. So that guy and that guy, because they're in opposite locations in these two separate fractions, are going to cancel. And I want to replace that with the unit I want on top. And because I have a nice conversion between millimeters and meters, I can just put that unit that I want right there. And now I actually have to go fill in this fraction with some of these values. Now there's two ways you can do this. If you like the scientific notation, you can use that, and how it looks is this. I'll show you both ways. If you're using the scientific notation, or the 10 to the various powers, all you do is you take the symbol that you've got here and replace it with your factor. So milli means 10 to the negative 3. So if I went from millimeters to meters, I replace the milli with 10 to the negative 3 up next to the meters. It's one way to look at this. So I'd say, okay, well, my 165 millimeters times 10 to the negative 3 meters over 1 millimeter, and I just multiply across the top. So it's going to be 165 times 10 to the negative 3. For those of you who haven't spent a lot of time playing with scientific notation in your calculator, I've got a bunch of them. You're going to need to be familiar with your own. Here's how I would punch that in. So I'm going to have 165. I'm going to multiply that by 10 to, on the Casios, I quite like these calculators. If you're looking to buy a new one, this is a good one to get. My exponent button's right there. I'm going to have negative 3. You need to make sure you actually use a negative button, not the subtraction button. And on this calculator, it'll just convert it to a decimal for me, and I'm going to get 0.165. And the units that are left, because I've canceled out my millimeters, are just those meters. So 165 millimeters is 0.165 meters. Questions about what I've done? Okay. Let's do another one. Let's make them more interesting. I want to convert 380 centigrams to milligrams. So again, the way this method works is I'm going to have my 380. I'm going to have they are centigrams, and I'm going to multiply that by fractions to try and convert this thing into a milligram. Now in the factor label method, because I'm going from a unit with a prefix to another unit with a prefix, we actually need to go through that fundamental unit gram. There is no nice conversion between centigrams and milligrams. So what I'm going to have to do is I'm going to have to multiply the centigrams in the numerator by centigrams in the denominator. I'm going to take that prefix and I'm going to get rid of it. I'm going to turn it straight into grams. And then I can go from grams. Now I've got grams in the numerator, which I don't want. So we're going to multiply by another fraction that puts grams down in the denominator. And I'm going to convert that into the units that I'm looking for. And so if you fill out your fractions with the units you're trying to cancel and create, you should, before you even put any numbers in here, you should see what happens. I had centigrams in the numerator, and now I've got them in the denominator, they're going to cancel. I put grams in the numerator and in the denominator, so they're going to cancel. And I'm going to end up with milligrams in the numerator, which is what I want. This exercise is what we call dimensional analysis. We're looking at the units that we're going to be working in before we even put numbers in. And now I'll show you what it looks like to use these fractions instead. How this works is this. If I've got a gram, instead of using the scientific notation of it, I'm going to use these instead. 1 gram is how many centigrams? Well, if I go back and take a look, yeah, because a centigram is 1/100th, that means that 1 gram is 100 centigrams. So now instead of using the scientific notation factor, we're using the fractional factor. And likewise, if I've got milligrams and grams, 1 grams is how many milligrams? Well, a milligram is 1/1000th. So then 1 gram is going to be 1,000 milligrams. So whichever of these you're more comfortable with, I don't particularly care which one you use. You just need to pick a set of values that you're comfortable working in. Either the scientific notation, or the powers of 10, or the fractions. You pick one of those and be comfortable with it. Get yourself comfortable with it. So then we've got a bunch of fractions. We're just going to multiply across the top. We're going to multiply across the bottom and simplify. So what I'm going to get here is 380. I've canceled all my units already. Mm-hmm. No, ask the questions. This is, yeah, feel free. Because we don't like, so we have to, the way the prefixes work is they're all related to some base. It might be the same as the fundamental units in the scientific international system. It might not be. So the fundamental for mass was kilogram, but kilo has its own prefix. So when we're converting, we have to deal with it without the prefix. We have to use the gram instead. So the way the prefixes work is in the scientific system, it's all based on powers of 10. So if we're going from one prefixed unit, so centigrams, to another prefixed unit, the way the factor label method works is we always have to go through whatever the unit is that has no prefix. Because the prefixes are all related to the unit, the prefixless unit, if that makes sense. So centigrams is going to go into grams, and we don't want grams, you're right. We're immediately going to get rid of the grams and go into milligrams. So what's going to end up happening here is if as I multiply across the top, we're going to multiply this by 1,000. And then because 380 times 1 is 380 times 1,000. And now I'm going to go across the bottom. 100 times 1 is just 100. And the beauty of the the scientific international system is that because they're all powers of 10, these things are going to often simplify really nicely. 1,000 divided by 100 is 10. Those zeros are all going to cancel, and so we're going to get 380 times 10. Multiplying by 10 just adds a 0, and so we're going to get 3,800 milligrams. Brad, does that make sense? Okay. But this method works even for some more gross stuff, so let's look at something more interesting. We're going to convert meters per second to kilometers per hour, and this is one that we do all the time in physics. So I'm going to show it to you once using the factor label method, and then I'm going to show you a shortcut so we never have to do it again. So meters per second to kilometers per hour and back again is going to look like this. I've got 24 what? Well, 24 meters per second, and I'm going to write it as a fraction because meters per second is a fraction. It's a compound unit. It's got a length in the numerator. It's got a time in the denominator. And I want to multiply by a bunch of fractions, however many fractions I'm going to need to multiply by, to convert both of these units simultaneously into a new set. The meters is going to go into kilometers, and the seconds is going to have to go into hours. If you write it out like all in one shot, like I'm trying to show you guys, then it doesn't matter what order you choose to go in. The easiest one to start with is what? Seconds to hours or meters to kilometers? You want to go meters to kilometers? Okay. So then we're going to multiply that thing by a fraction. Because the meters is in the numerator of the meters per second, then meters is going to go where in this fraction? It's going to go in the denominator. And because this thing has no prefix, it's just a meter, it can go straight into a new prefixed unit. It can go straight into the kilometer. Now, you can choose to whichever one you want to use here. We can use the powers of 10, or we can use the fractional values. It doesn't matter to me. It depends on how you think it through. What's the relationship between kilometers and meters that you are most comfortable working in? If I ask you for that conversion, what does your head immediately go to? 1,000. Okay, so Brad, you're telling me that there's 1,000 what where? Okay, so if that's where your mind immediately goes, and I'm willing to bet that's where most of you went, then you'd say, well, 1 kilometer, you'd put the 1 up next to the kilometer, is equivalent to 1,000 meters. So the 1,000 would go on the bottom with the meters, and the 1 would go in the numerator with the kilometers. And this is typically how my Canadian students think things through. It's usually if we're using the powers of 10, those tend to be my European students. For whatever reason, seem to gravitate that way, at least in the past they have. So at this stage, if we look at what we've done here, my meters are going to cancel. I want something with kilometers in the numerator, and we've got that, so we're good. There's nothing more we need to do with our length units. So we can multiply this by a bunch of fractions now to get rid of the time. I want to take seconds and I want to convert it into hours. Does anyone know a nice conversion to go directly from seconds to hours? Or is there a unit that you would tend to go through? Sorry? It would make a lot of sense. If that's what you're most familiar with, then yeah, let's go through minutes. So if I've got seconds on the bottom now and I want to get rid of them, where am I going to put seconds in my fraction here? Put them up top. The opposite side of where they were. And it's been suggested that we go through minutes. That makes a lot of sense. And before we fill in these values, let's finish the fractions. We can use the units to see we're not done yet. We have a nice conversion from minutes to hours, so I'm going to put those in my second fraction here. Minutes is going to go where in this fraction? Now it's going to go up top. And my hours is going to go down on the bottom because that's where I want it to end up. At the end of the day, what I want to have here is a kilometer per hour, because my hours are going to go in the denominator. And so now I got to fill in these values. How are seconds and minutes related? There's 60 seconds in 1 minute, so the 60 goes with the seconds, the 1 goes with the minutes. And the minutes and hours are related how? There's 60 minutes in 1 hour. So my seconds are going to cancel here, my minutes are going to cancel here, and I can see that all I'm going to have left is kilometers in the numerator and hours in the denominator. I really should have left myself some more space. So I'm going to wipe this out. And I'm going to move it over. And now to actually do the math, I'm just going to multiply across the numerator, multiply across the denominator. In the numerator, I'm going to have 24 times 60 times 60. And in the denominator, I'm just going to have 1,000 times 1 times 1. Now, I'm showing a lot more work here than I would necessarily expect from you. At this, if you showed me this and then just punched it through your calculator, that would be totally acceptable. I don't need to see this, but I'm going to make a point here in a second. So humor me this time and write this bad boy out. If we calculate this out, what is 24 meters per second in kilometers per hour? What is that value? Yep. Starting them easy. What's up? Okay. Okay. Sure. Yeah. Yeah, easy.
We got each other.
Yeah. Brian sent out an email about department meetings with Jenny. Do you know anything about that?
Yeah.
Okay. Are we going to discuss mathy things before you meet with her, or
Give me the words. Yeah.
just the booklets is all I'm concerned about?
I already got a good answer for you.
She gave us one? Oh, sweet. Let's talk
I
tomorrow.
was just holding on to it until better.
Let's talk tomorrow.
A day when you needed it.
Today's been pretty good, so I don't need it today, but hang on. Okay.
It's really bad news.
Really bad news.
Yeah,
Okay. Really
Same.
bad. Okay. What's that value? 86.4. So your brain's not used to operating in meters per second. 24 meters per second. 24 doesn't sound like a very large number, but if you think about how big a meter is and how quick a second is, this is pretty quick. It's just under highway speeds, or if you're driving to Mission, it's probably what you're driving because the speed limit's 80, so you're probably speeding a little bit. So 24 meters per second is equivalent to 86.4 kilometers per hour. This conversion we do all the time in this course, especially in the first chapter. So this piece right here, we are going to simplify. The simplification is going to look like this. 6 times 6 is 36. So 60 times 60 is 3,600. And 3,600 divided by 1,000 is 3.6. 3.6 is a nice simple number to remember. And so as we go forward, if I'm asking you to convert between meters per second and kilometers per hour, this is the only value I need to see. I'm not going to make you do this work more than once. So if we're going from meters per second into kilometers per hour, and that's what's going to go on over here in this box. If I've got meters per second, I'm going into kilometers per hour. If we look at what happened here, the 3,600 was in the numerator. 3,600 divided by 1,000 is 3.6, and I multiplied by it. So we go from meters per second into kilometers per hour, we're going to multiply by 3.6. So to go the other way, the opposite of multiplication is division. And so this box, I'm not going to give you, it doesn't show up anywhere on your formula sheet. But should you want to memorize this, it'll make these conversions go super nicely moving forward. Okay. I'm going to give you a chunk of time. I want you to play with these. I have a bunch of conversions here for you. Obviously, I'm not expecting you to cram your work into this space. So I did tell you yesterday, and lots of you did grab the coiled books that I have. Grab whatever, whether it's your own line paper in your binder or it's the coiled books that I gave you yesterday. Work through these. Let me know if you need a hand with the method. I want to see you practice the method. Even if there's nice, quick, simple conversions, having a handle on the larger method is going to make your life so much easier. If you're grabbing a calculator, don't put your phone on my desk. Put it in the slot you took the calculator out of. Yeah, do what you got to do. Oh, I just put your name on the board. I will give you a chunk of these answers. Lots of you have made very real progress. I want to add one more thing to the bottom here. It says, how long in hours, for question 3B. 3B says, how long in hours will it take you to count to 1 billion, counting one number every second? I want that answer, I want in hours and years. How many years would it take to count to 1 billion if you count to 1 billion once every second. Hello, what's going on? Yes, leadership, you can make an announcement.
Okay, hi guys. During February 13th, we're having auditions, or no, we're having about talent. But we're looking for people to audition and performing a talent show. It would be February 36. So for anyone who wants to show talents like singing, dancing, piano, rapping,
Magic tricks.
anything that you want to show off, you can show off.
Math.
We'll have a drop-in audition at Miss Black's stage area where the dance is held at lunchtime at February 3rd to 6. And the actual play or at least like how will be February 3rd. Any questions?
Judy, come here, really fast. Yes, go to the washroom. Okay, I'm gonna give you guys the answers to the first set. There they are. Okay, here's your first chunk, A through H. I'll give you the second chunk as well. Hands up for those of you who are done. Question 2. Is anyone done question 2? All of question 2? Fantastic. I'll give you that chunk as well. 3,700, 7,000, 470, 0.47, 50,000. That should be 1,800,000. G is going to be 1.8. And I'll give you the answer to question 3 tomorrow. If you haven't already, the values are ridiculous. Flip the page real quick. I'm going to give you this is optional extra practice. I've included it because students sometimes ask me for more. If you'd like more practice, here they are. The answers for those are right here. Work on it if you would like. I would like to do a quick review of scientific notation. Okay. With what little time I have left, let's go. So, scientific notation. We've already kind of used it. It's wildly useful, horrendously important. What's it for? Does anybody know? To make big numbers. When you say look pretty. Cool, I'll say that. Make big numbers. Oh, and well, the same is true of the small. And small numbers more condensed. Two examples that I have for you here are these two numbers, 299,792,458 and 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000kay, does anyone recognize either of these two numbers? No, it is not pi. Nobody recognizes either of these numbers? Okay, this guy here more often shows up like this. I'll convert it into scientific notation for you. Here's how you would convert this thing to scientific notation. You start where the decimal is, and then you move the decimal, and it jumps until you just have one digit left in front. So this thing would be 2.99792,458 times 10 to the, however many times you jumped left, is the value of the exponent up here. So we jumped 1, 2, 3, 4, 5, 6, 7, 8 times to put the decimal place between the 2 and the 9. So this would be times 10 to the 8. That number hasn't been overly condensed at all, really. So we're going to round this thing. Often this number shows up as 3 times 10 to the 8. 2.99 rounds to 3. So does this number look even remotely familiar to any of you? 3 times 10 to the 8? Nobody? No, my Germans? My Spanish students? Nothing? Okay. This number has units of meters per second, means it's really going really fast, whatever it is. It's the speed of light. This is the universal speed limit. Nothing goes faster than this value. If it does, if you decide to study physics and you discover something that breaks this value, you will immediately win a Nobel Peace Prize, or they will find all sorts of problems with your work. Nothing goes faster than this value. And there's this value. This number is ridiculous. There are 33 zeros here. So then we need to jump it one more. There's 33 jumps there. And then one more jump takes us to 34 jumps. So this number, the scientific notation most often shows up with really small values. This value gets rewritten as 6.62607015, still less than writing 33 zeros, times 10 to the negative 34. When you move to the right, that exponent becomes negative. And this number I don't necessarily expect any of you to see unless you've done some ridiculous reading. This is what's called Planck's constant. And it is a fundamental value in the fabric of the universe. So crash course on scientific notation, or a review, because you may not have seen it since grade 9 or middle school. When you are converting a value into scientific notation, you move the decimal point until only one leading digit remains. So for this one, we moved it left until it was between the 2 and the 9. This one, we moved it right until the 6 was in front. And that leading digit needs to be non-zero. So one leading non-zero digit remains, and the number of spaces moved is the exponent. You move left, the exponent is positive. If you move to the right, the exponent is negative. So for example, actually, I've done my 2 examples. This guy, the decimal starts, if there is no decimal, started at the far right edge of the number. And if you're moving left, exponent becomes positive. If you're moving right, the exponent becomes negative. Now, the opposite is true if you're going the other way. I'll just do one example here of taking things out of scientific notation. If you're putting into scientific notation, these are the rules. If you're going out of it, it's the opposite. If I'm going 5.5 times 10 to the negative 4, that negative exponent means I moved right to get here. So if I want to undo the scientific notation, I have to go the other way. So this thing means if I have a negative exponent, I move the decimal to the right to get here, so I got to go the other way. I'm going to start with my 5.5, and I'm going to move this thing back 1, 2, 3, 4 times. And then every empty jump is going to get a 0. 1, 2, 3. So then this value would 5.5 times 10 to the negative 4 is 0.00055. Going the other way, I mean, if the exponent is positive, I moved to the left to get here. So to undo that, I'm going to move to the right, and I'm going to add a whole bunch of zeros every time there's an empty jump. I'm going to leave these 1, 2, 3, 4, 5, 6 questions to you as part of your homework, in addition to that very first page of unit conversions. And for these guys, I'm going to see what you can do with them without a calculator, if you can. I would like you to compute the following. And you need to use your exponent laws. That's the beauty of scientific notation. is you can multiply very large numbers and very small numbers easily using these exponent laws. If I have the same base and I'm multiplying, what's the exponent law there? I'm adding. So if I have 10 to the 3 and I'm multiplying by 10 to the 5, this thing's just going to be 10 to the 8. So for example, I'm going to I'll look at E, and then we'll free you to play with this stuff. If I have 3 times 10 to the 8 squared, this means I have 3 times 10 to the 8 times 3 times 10 to the 8. Now, you can multiply in whatever order you want, so let's change the order. I'm going to rewrite this as 3 times 3 times 10 to the 8 times 10 to the 8. If it's all just a bunch of multiplication, the order you have it in doesn't matter. So 3 times 3 is 9. And then the 10 to the 8 times 10 to the 8 is 10 to the 16. When I multiply same bases, I add the exponents. So this is just going to be 9 times 10 to the 16. So you can multiply really large numbers really quickly using these scientific notation and exponent laws. So that's it for today. You've got 8 minutes to the bell. Use the time. Finish whatever you didn't finish on that first set of unit conversions. If you want the second page's practice, you've got it and the answers. And then I want you to practice playing with the scientific notation and exponent laws here. And that's it for me for today. Work to the bell. When the bell goes, you make it out of here. Have a great day. See what you can do with these. If you borrowed a calculator from me, don't forget to take your phone back as you exchange them.
Me, please use the washroom. 8 minutes, buddy.
I was going to say 10-10 means I can't send you. Are you dying, Kai?
No, he's not.